Today we're going to talk a little bit about the photoelectric effect. We'll get to the math on it, an equation, and actually doing problems with it. Um, I Originally, my plan was in that part two of the lab, students would play with the simulation and discover the photoelectric effect. So there's a short little lab where you sort of use the simulation, saw that frequency or wavelength seems to affect the energy. And then part two of the lab was a guided thing where you kind of work through using the simulation to discover all the work that's about to be outlined in this note. So I realize it's a little bit repetitive, and some of this you'll have seen before. Just I'm kind of modifying how we do it. And to save time, some of you aren't doing that part two of the lab. So for some of you, this is repetitive, and for some of you, this won't be. Often when talking about energy, I use the analogy of money because like energy, money can switch from like one account to another account, just like energy can change from one form to another. So another money analogy to help make sense of photoelectric effect. If you were to go into a store with $5 trying to buy something that costs $7, that's not going to work. You don't have enough money. You don't meet that threshold of the thing you want to buy. But if you went into the store with $10 and wanted to buy the $7 ball or whatever it is, then you can do it. You've met the threshold and you've got some left over. If you were to go into the same store with $20 to buy the same $7 object, you meet the threshold and you have even more money left over. That's kind of a nice little analogy for what the photoelectric effect is and the little equation that we'll run to make sense of it. Photoelectric effect confirms the particle model of light, which is a little bit weird. We've got experimental confirmation that light is like a particle. We'll come back and talk about the wave model. We'll do that next. We'll deal with that. So for now, hopefully this is a little bit weird. In last unit in interference, we said light was a wave, and now I'm telling you that light is a particle. So hopefully it's a little bit weird, but we'll come back and we'll deal with the weirdness once we firm up photoelectric effect. Basically, photoelectric effect is cool, simple little equation, E equals HF, or if we flip the F out of there, E equals HC over lambda. What that says is if you have light of a particular wavelength, every little particle of that light is going to have the exact same amount of energy. So if we had blue light, plug in the wavelength for whatever shade of blue you're interested in, crank out HC over lambda, you're going to get this tiny value of energy. That represents how much energy one particle or one bullet or one photon of that light would deliver. You couldn't have, and sorry, all of that light of that wavelength, its energy is delivered in multiples of that. So if the number worked out to be a number like 3, the energy of that light could be 3, 6, 9, or 12, but it couldn't be any number in between. It's quantized on the value of the energy you get from HC over lambda. And each particular wavelength would have its own particular base amount of energy. All right. If you played with a lab, or if you haven't played with a lab, spend some time on the simulation, and I'm going to talk you through hopefully what you could have seen. There is something called the work function. It is, and if you play with a lab, play with the simulation, you'll notice that there's a wavelength, a longer wavelength, at which point electrons aren't ejected. And as you get to shorter and shorter wavelengths, eventually you'll get to a wavelength where electrons are ejected. Basically, from our equation E equals HC over lambda, a long wavelength has a low energy. It's an inverse relationship, so big wavelengths, small energies. If the energy is too long, then the energy is too low and electrons aren't ejected. That energy you have to match, that threshold energy, that you have to have at least that much energy to free an electron, that threshold energy is called the work function. And every metal would have its own value of the work function. So in that simulation, if you clicked on the one plate, you could toggle between like magnesium and cesium and silver between different metals. The difference would be each metal would have its own work function. The work function is kind of like the cost of the item that you went to buy. If you went to the store with $5 to buy a $7 item, $7 is like the work function, $5 is below that, you're not going to be able to buy it. But if your light has more energy, then an electron is ejected. Then you could buy the thing. That's kind of like having more than the work function. If you have $10, you could buy the $7 item. As long as the light has more energy than the work function, then electrons will be ejected. If the light has a lot more energy than the work function, then those ejected electrons are going to have a lot of kinetic energy. The leftover amount of energy shows up in the kinetic energy of those electrons. So $10 beats 7 by a little bit, but if you had $20, that beats 7 by a lot. That extra, in this case, in this analogy, that leftover, the bigger the leftover, the more kinetic energy. If you were to go back to the simulation to find a work function, pick a metal, and then just scroll through the wavelengths or toggle through the wavelengths and find the longest wavelength that doesn't eject electrons. Once you figure out what that longest wavelength is, then you can find the energy of that wavelength by using Planck's equation. So if you needed to know the work function experimentally, you could find it by experimenting with the wavelengths. The longest wavelengths that don't eject an electron, they would mathematically tell you the energy of the work function. Gonna keep rolling along in one big video. The kinetic energy of the ejected electrons is next. Actually, I'm changing my mind. Here, take a break, look at the simulation and work through this little thing. See if you can figure out how to figure out the kinetic energy of the ejected electrons. And instead of me doing twice the work, once you play around and follow these 3 steps, then watch this video because it explains what I was hoping you would see when you work through those 3 steps.